Hello everyone, I'm Neeraj Kumar from CSCB section. Welcome to my presentation regarding wavelet matrices. Let's discuss about wavelet transform and wavelet based numerical method. Wavelets are already recognized as a powerful new mathematical tool in signal and image processing, time series analysis, geophysics, approximation theory, and many other areas. First of all, wavelets were introduced in seismology to provide a time dimension to seismic analysis, where Fourier analysis fails. Fourier analysis is ideal for studying stationary data whose statistical properties are invariant over time, but it is not well situated for studying data with transient event that cannot be statistically predicted from the data past. Wavelets were designed with such non-stationary data in mind. Their generality and strong results have quickly become useful to a number of disciplines. The wavelet transform has been perhaps the most exciting development in the decade to bring together researchers in several different fields, such as signal processing, quantum mechanics, image processing, communication, computer science, and mathematics, to name a few as in one. Today, Wavelet is not only the workspace in computer imaging and animation, they are also used by the FBI to encode its database of million fingerprints. In future, scientists may put wavelet analysis for diagnosing breast cancer, looking for heart abnormalities, predicting the weather, signal processing, data comprehension, smoothing, and image compression, fingerprint verification, DNA analysis, protein analysis, blood pressure, heart rate, and ECG analysis, finance, internet traffic description, speech recognition, computer graphics, and many others. Some applications of wavelet transform are described at the end of this paper. Wavelet analysis provide additional freedom as compared to Fourier analysis, since the choice of atoms of the transform deduced from the analyzing wavelet is left to the user. Wavelet theory involves representing general functions in terms of simpler building blocks at different scale and position. The fundamental idea behind the wavelet transform is to analyze according the scale. Now let's discuss about the history of wavelet transform. The concept of wavelets or condoletes started to appear in the literature only in 1980s. This new concept can be viewed as a synthesis of various ideas which organized from different disciplines including mathematics, physics and engineering. In 1982, Jean Marlet, a French geophysical engineer, did not plan to start a scientific revolution. He was merely trying to give geologists a better way to search for oil. Petroleum geologists usually locate underground oil deposits by making loud noise because sound waves travel through different materials at different speed. Geologists can infer what kind of material lies under the surface by sending seismic wave into the ground and measure how quickly they rebound. It may be salt dome, which can trap a layer of oil underneath. Figuring out just how the geology translates into a sound wave is a tricky mathematical problem, and one that engineers traditionally solve with Fourier analysis. Unfortunately, seismic signal contains lots of transients, abrupt changes in the wave as it passes from one rock layer to another. Fourier analysis spreads out that spatial information all over the place. Now let's discuss about the preliminaries of wavelet transform. In this section, we will discuss the preliminaries of wavelets which are useful to understand wavelet transform and its different classes as continuous and discrete wavelet. Wavelet may be seen as a complement to classic Fourier decomposition method. Suppose a certain class of function is given and we want to find simple functions f0, f1, f2 such that f of x is equal to sigma n is equal to 0 to infinity an into fn of x for some coefficients alpha n. Wavelet is a mathematical tool used for representation of the type 1 for a wide class of function f. Alternatively, we can define wavelet as a wavelength means a small wave. The sinusoids used in Fourier analysis are big waves, and in brief, a wavelet is wave-like oscillation with an amplitude that starts from zero, increase and then decrease back to zero. Equivalently, mathematical conditions for wavelet are integral minus infinity to infinity mod of phi t whole square dt less than infinity, integral minus infinity to infinity mod of phi into t of dt is equal to 0, integral minus infinity to infinity mod of phi bar into omega by mod omega whole square d omega less than infinity, where phi bar omega is the Fourier transform of phi of omega. Equation 4 is called the admissibility conditions. Now let's discuss about the wavelet transform. Wavelet means small wave. So wavelet analysis is about analyzing signal with small duration finite energy function. They transform the signal under investigation into another representation which converts the signal into a more useful form. This transformation of the signal is called wavelet transform. Note that in case of Fourier transform, spectrum is one-dimensional array of value, whereas in wavelet transform, we get a two-dimensional array of value. Also note that the spectrum depends on the type of wavelet used for analysis. Mathematically, we denote a wavelet as phi of AB of t is equal to mod of root of mod A into t minus b. A comma b belong to R, A not equal to 0, comma 5, where b is location parameter and A is scaling parameter. For the function to be wavelet, it should be time limited for a given scaling parameter. We translate the wavelet by varying the parameter b. We define wavelet transform as w of a comma b is equal to integral of t of f of t. For every a comma b, we have wavelet transform coefficient. If mod a less than 1, then the wavelet is compressed version, small support in time domain of the mother wavelet and corresponds mainly to higher frequencies. On the other hand, when mod a greater than 1, then phi of a comma b of t has a larger time width than phi of t and corresponds to lower frequencies. Thus, wavelets have time widths adapted to their frequencies. This is the main reason for the success of Morlet wavelets in signal processing and time frequency signal analysis. Our next topic is wavelet families. A wavelet system consisting of a scaling function phi of x and the wavelet function phi of x. In literature, several wavelets with different properties have been derived in references and few of them are described below. Haar wavelet with orthogonal compact support, Diverge's wavelet with different compact support, Coiflet wavelet with different compact support, Bloch-Spine semi-orthogonal wavelet, Battle-Lemaire's wavelet, bi-orthogonal wavelets of Cohen, Shannon's wavelet, and Mayer's wavelet. Mayer wavelet is continuous and discrete transformation with infinite regularity. Gaussian wavelet is discrete transformation with infinite regularity. Mexican hat wavelet is continuous transformation with infinite regularity. Morlet wavelet Morlet wavelet is continuous transform with infinite regularity. Multi-resolution analysis. The wavelet basis induces a multi-resolution analysis on L square of R, that is, the decomposition of Hilbert space L square of R into a chain of closed subspaces, such that U of Vj is equal to L square into R. By defining the Wj as an orthogonal component of Vj and Vj plus 1, Vj plus 1 is equal to Vj plus of Wj. The space L square of R is represented as a direct sum of Vj's as L square of R is equal to Wj. Connection coefficients. Any numerical scheme for solving differential equations must adequately represent the derivative and linearities of the unknown function. In the case of wavelet basis, these approximations give rise to certain L2 L square inner product of the basic function. Their derivatives and their translates called the connection coefficients, which are defined as the formula given in the slide, where di is the number of differentiation of scaling function phi I with respect to x, which gives rise to the t-term connection coefficients. Kent et al. 15 have represented an efficient algorithm to calculate the coefficient in a bounded interval. That's all for now, friends. This is end of my presentation regarding wavelet matrices. I hope you enjoyed and gained a bit knowledge regarding wavelet matrices. Thank you.